All right, folks, so I guess we'll get started. So I started recording this session, so agree to that, and I will post it after we're done here today at 8 before I go home. All right, so as you see, I'm taking requests, should we start with chapter 1, 2, or 3? It sounds like folks want to start with 3, chapter 3, and then we'll go back to 1, and then chapter 2. Keep in mind the length of each of the chapters. I think if you recall, chapter 1 was over, 100 slides. Chapter 2 was maybe 40, and chapter 3 was about maybe 50 slides. So keeping that in mind and all the topics that we learned in each chapter, that will reflect, the amount of time we spent will reflect the questions that you see on the midterm. So before we get started, I want to make sure everybody has their periodic table. They should have that in front of them, their calculator, and hopefully your iPad. I don't know what you're watching on, hopefully a computer. So hopefully you have downloaded, the Zoom midterm packet. All right, so I put together a packet for questions similar to that, what you might see on the exam. So to find that, you can either go to my announcement, which takes you to the page where you found this link. So wherever you found this link, I have that packet, and it's on this page that you got the link. That's where I will post the key and the recording afterwards. All right, okay, so here is the packet. Let's send it to Zoom, and we will, Notability, and we will get started. Okay, so let's go. Okay, where did I put it? There we go. All right, so let's start on chapter 3 stuff. Naming. Okay. So here on page 7 is where chapter 3 material starts. So I will just start with question 21 first. All right, so based on the octet rule, nitrogen can form what? A cation or an anion. So from what I recognize and some of the topics and concepts that we learned is that metals and nonmetals behave differently. Metals on the periodic table, so the left side of the periodic table, those are metals. They typically form cations. They typically lose electrons to achieve their octet. Nitrogen specifically is a nonmetal. All right, so we can predict that nitrogen will probably form an anion, which is negatively charged. All right, so you could, if you wanted to, practice your own understanding, you could change this word nitrogen to any other element, one of our main group elements, and you could write the same things here. And so we predict that it's an anion because it can gain electrons to achieve its octet. And so specifically, we need to figure out how many electrons it gains to achieve its octet. So based upon where nitrogen is on the periodic table, if you look at your periodic table, the main groups, the group numbers increase from 1 is where hydrogen is. Okay, you can't see that. Okay, my ring light is too strong. The second group is beryllium. So there's our alkaline earth metals. Then it skips over the middle of the periodic table. So period 3 is boron, carbon is 4, nitrogen's 5, oxygen is 6. And so if we go back to nitrogen, nitrogen is in group 5. So that tells us something about the charge that nitrogen can make. So the equation that we use to predict anion charges is the anion charge equals the group number minus 8. All right, so if we plug in 5 into that equation, 5 minus 8, nitrogen will make a -3 charge anion. So we would write that something like that in an ionic compound. And the name of this, because it's monoatomic, would be nitride. All right, and so that's how you go about it. We could change this question. Instead of nitrogen, we could say, what about fluorine? If we did fluorine. Fluorine is also a nonmetal, so it would produce an anion. Since fluorine is group 7A, we use the same equation. Group number 7 minus 8 is -1. So fluorine as an anion will be F-, and it has the name fluoride. So there we go. There's 2 questions in one. And just to kind of round out things, we can predict anion charges. Group number -8 is the anion charge. If we wanted to do a cation example, cations, so metals, keep in mind, metals will always, their charge will be their group number. So let's just do a quick example of something that would be a cation. So something like magnesium. All right, so if I change this question to magnesium based on the octet rule, magnesium would form a cation because it's a metal. It would adopt a charge of magnesium 2+ because it's in group 2A. And the name of it would just be magnesium ion. Magnesium ion. Okay. We getting that? No questions? Okay, let's keep going. Let's keep going. All right, so in which of the following pairs of polyatomic ions do both members have the same charge? So we're looking for the same charge. So these are all polyatomic ions. So these are things that you need to memorize. All right, so if you remember that table of all of those polyatomics, you just need to memorize them. So with these polyatomic ions, it's not so much you can predict them off the periodic table. It's the formulas and the name and the charge is something you need to memorize. So within this example 21, you can predict most of the charges, the name of monoatomic cations and anions when there's just one element or one atom present. But with polyatomics, you really just have to memorize it. And if, my suggestion for memorizing it is just practice naming. Once you see it enough, you will know that sulfate is SO4 2- eventually. All right, so really all this is identifying the names and charges of all of these compounds. So let's do that. So ammonium is the formula NH4. That is the one cation polyatomic that you need to memorize. Most of the polyatomics, the majority of them are anions, and hopefully you recognize that in the list that you see. So ammonium is a +1. Phosphate is PO4 3- based upon the thing. What is the difference between monoatomic and polyatomic ion? So these two substances I just drew, NH4 plus PO4 3-, these are both polyatomics. Well, everything here is polyatomic because there are multiple atoms in that whole thing is charged. That whole NH4 is charged. So we went over Lewis structures today. What NH4 would actually look like? It's built like a covalent compound. So you could go ahead and count all of the valence electrons and you would get a shape that looks like this, a nitrogen with 4 bonds with hydrogens, but that entire thing is positively charged. All right, so those are polyatomics, that this whole group of bonded atoms are charged. In this case, for ammonium, it is positively charged. But with these guys in question 21, magnesium, it's just a magnesium atom. That happens to be charged, all right, with subtract 2 electrons from the neutral atom. So this magnesium would have 10, sorry, not 10. It would have 12 protons and 10 electrons in order for it to be charged, but it's just one atom. So monoatomic naming has a different set of rules, the ones we just went over in 21, where 22 polyatomic ions, not so much not so much predicting based upon the periodic table, but definitely just memorizing. Okay, so hopefully that answered that question. Okay, so let's keep going. So all these polyatomics will have chemical formula that go along with them. So we can see here that ammonium and phosphate, nope, they don't have the same charge. So it's not that one. Sulfate is SO4 2-, nitrate is NO3-. So again, not the same charge. Hydroxide is OH-. Carbonate is CO3 2-. So again, not the same charge. Hydroxide and ammonium. So we did these ones already. So hydroxide is OH-, ammonium is NH4+. So you see here that it's like -1 and +1, but that's still not the same charge because one's an anion, one's a cation. So that is not correct. So it's the last one, chlorate and nitrate. It's ClO3 minus and nitrate is NO3 minus. So the answer here would be E. So really that is identifying, from the name, can you recall the formula and the charge? So that's just another way to ask it. I could ask a question like, what is the name of sodium nitrate, or sorry, what is the formula of sodium nitrate? So if I asked a question like that, what is the formula for sodium nitrate? It's a different kind of recall where we just have to determine the charge of that polyatomic. So in this case, nitrate is NO3, but then it's also attached to a monoatomic cation. In this case, it's sodium. So we need to recall our monoatomic naming rules and the charges that go along with them. And so you should recognize that sodium is a group 1A element, so it will adopt Na+. And then the full chemical formula would be those two ions smashed together into a neutral compound. And so in this case, since it's just 1 minus and 1 plus, it would just be sodium nitrate. Where we don't have the charges, it's just one of each. Okay, so I like to ask multiple questions in one question. Okay, so which of the following neutral atoms is incorrectly paired with the number of valence electrons? So our whole idea with predicting charges of monoatomic ions up here, where we got these two formulas where your cation charge is your group number, your anion charge is your group number -8. This comes from the idea of valence electrons, how much a neutral atom has. So like, for example, nitrogen has 5 valence electrons. It wants to have 8. So that's why it gains 3 additional electrons to become nitride N-3 as an ion. So these are, in my mind, these are all the same question, kind of thinking about predicting monoatomic charges, just kind of like in a different way, and recognizing it all comes from the periodic table. These really aren't things that you need to memorize, except when it's polyatomic. Jackson, I am already recording. So within these, so it's trying to say, okay, here are the names of the elements when they, based upon where they are on the periodic table, we should be able to predict the number of valence electrons. So the number of valence electrons for main group elements is essentially just the group number. It's the group number. But do recognize where the group numbers come from on the periodic table, where it starts with 1 is on hydrogen, all the way to helium and neon, that's group 8 within there. So fluorine would be group 7. So some periodic tables are a little bit different, where it goes 1, 2 is beryllium, boron becomes 13. But do realize that boron starts group 3. Carbon is group 4A. Usually when I talk about groups 1 through 8, I typically have A at the end. Where can we find the specific periodic table we can use on the exam? It is on the My Midterm Preparations page, where I have all those practice midterms. I have the exact copy of the exact supplemental information packet you will receive. Okay, I'm gonna exit out of these questions so we can keep going. Okay. Oh wait, no, hold on. You would. Okay, done. Okay. Okay. All right. Did we answer this question yet? No. All right. So really this question is saying, do I have the right group number for these elements? So we look at rubidium. Rubidium is in group 1A, so that is correct. Sulfur, we look at the periodic table, is group 6A. So yes, 6 valence electrons. Boron is group 3A. See, these numbers have meaning. They have meaning, guys. It's number of valence electrons. Bromine, 7 is 7A. So yes, phosphorus is group 5A. So here's the incorrect one. All right. So if you are thinking, okay, why 3 valence electrons, what I'm trying to, I guess, trick a student to choosing is seeing that, oh, phosphorus within like this block. Okay, you can't see that. can't see that. Okay, within like this block, it's 3 over, but you have to include these elements too when you count over. What compounds do we need to memorize? You need to memorize your polyatomic naming scheme, and then building the molecules or your ionic compounds. There really isn't any memorization there. It's, can you build a neutral molecule? All right. Okay. All right. So let's keep going. Valence electrons. And then from there, we can also predict the charge that most of these things would make, right? Depending if it's a non-metal or a metal. Why don't we do that? Want to do that? Let's think about what these substances would make if it was a monoatomic. If it was a monoatomic ion, what would it make? Hopefully I can do this. So rubidium, group 1A. If you see rubidium is a metal, it's on the metal side of the left side of the periodic table, right? So identify that as a metal. It's going to make a cation. Specifically, it will make a +1 cation because it's in group 1A. Sulfur is a nonmetal, so it's going to make an anion, so negatively charged. So we use the other equation where it's anion charge is group number -8. So sulfur will have adopt a charge of -2. Boron, this is a metalloid, so let's just skip that one. Right, so boron won't be in a ionic substance because it is a semi-metal. It's not a metal, it's not a non-metal, so we'll just skip that one. Bromine is a non-metal, it's on the non-metal side. It's in group 7A, so 7 - 8 is -1, so bromide would be Br-. And then phosphorus here is in group 5A, and it will gain 3 electrons because it's a non-metal, just like our nitrogen. So there is a table somewhere in chapter 3 that has all of those charges of the monoatomic ions, the main group elements. But again, you don't have to memorize those charts. You can predict all of it from your periodic table. So using the whole idea, those 2 equations where metals, your metal charge, which is a cation, is always equal to the group number. If you look at that table, I don't remember what table number it is, you'll see that all of your 1A elements make +1 cations. All of your 2A alkaline earth metals make 2+ cations because the your charge equals your group number. And then your non-metals charge, which are negatively charged, your anions, is always your group number -8. So when you look at that table, you can see these equations at play that build that table. So you don't really have to memorize it, not so much. You just can get it all from the periodic table. Okay. Are we good? Can we keep going? Oh, I forgot, you can't talk. You can't talk. So I just look at I just look at myself and I pretend I'm teaching myself. All right, so the next question, what is the chemical formula for the ionic compound that can be formed from the reaction between magnesium and fluorine? Will lecture notes from class be posted today? They're already, so the recording, you mean? The recording's already posted. I posted it after class. Okay, I'm gonna, yeah, all right. So 24. So we are building molecules, or so ionic compounds, based upon the identity of the things that its composition. So we have magnesium and fluorine. So I tell you it's an ionic compound, but 2, you should be able to look at this and be like, oh, this is a metal and a non-metal. This will make an ionic compound because metals make cations, non-metals make anions. It's a private video. That's weird. I'll have to look at that after this. It was, so sometimes when I post the video, I post the link before it's done loading. And so that might be it, that YouTube might still be rendering it. I don't know, but I'll take a look after this video. Can't do it now. So where am I? What is the chemical? Okay, so this is an ionic compound. So we need to make ions. So magnesium, it's all the same things. Again, We have to predict the charge of these substances and then combine them in such a way that gives us a neutral compound, just like we did with sodium nitrate. So we can predict, okay, if magnesium is going to make a ion, one, it will make a cation because it's a metal. Specifically, it's a 2A metal, group 2A, so it will make a magnesium 2+ cation. Next, fluorine. So when fluorine is an ion, it's a nonmetal, remember? It will make an anion or negatively charged substance. It's specifically group 7A. So we do anion charge equals group number -8. So fluorine will make a minus charge. All right. And so we just put those two substances together to make a neutral compound. So recognize that the charge on magnesium is 2+. So I actually need 2 fluorines to make it completely charge neutral. So if I combine those things, my substance will be MgF2. So to denote that there's 2 fluorines there, we have to use a subscript to indicate that I need 2 anions in this one unit, in this one ionic compound to make it charge neutral. And so note here that I got rid of the charges because the overall ionic compound is neutral here. So we don't need the charges anymore. So then there's our answer. Which one is it? C. It is C. So E would be if a student kept the charges, but you don't need the charges because the whole compound is overall neutral. For fun, let's just name it. Why don't we name it? So naming rules for ionic compounds, you name the metal and then you name the nonmetal with the "ide" ending. So this would be magnesium fluoride. All right, and so remember, in ionic naming rules, you never, in the name, why is it neutral? Because in order to make these compounds, ionic compounds, we always need to combine them in such a way for it to be neutral. We can't just put MgF together because that would not be a neutral compound. We would have a 2+ charge and a -1 charge. So that whole thing would actually be, +1 charge there. So this would be incorrect because the charges don't work out. We need to make sure when we communicate compounds that we communicate them as a neutral compound. All right. Can you provide us of writing a chemical formula with a polyatomic? Sure. So let's do another example. So there's a lot of questions in a row. So we say magnesium fluoride. So remember when I got really, really animated in class and I stomped my foot and I said, in ionic naming, you never, ever, ever have to tell the reader how many ions are in the name. You don't have to say magnesium and there's 2 fluorines. You do when it's molecular, but this is ionic naming, so it's completely different. And so within here, the name magnesium fluoride, from this name, we could still build the neutral chemical formula, because from the name, we can always predict the charge. I know magnesium as an ion is always Mg2+. I know fluorine, because of the "ide" ending, is always F-. From the name, I can always get the chemical formula with ionic compounds. You never have to say how many of each ion there are. That's only molecular naming. So in your brain, keep those 2 naming schemes completely separate. Ionic has one naming rules. Molecular has different naming rules where you do have to use the di, tri, tetra stuff, but not in ionic, because you can always, from the charges, predict from the name, you can predict the charges and therefore the chemical formula to make a neutral compound. Okay, I need to get rid of some of these questions so I can read them. Okay, I did the neutral one. Okay, yeah, we can do a polyatomic. When would you use 8? So monoatomic names always end in "ide." So in this example, it's just monoatomic atoms, meaning that it's just a magnesium atom becoming an ion and a fluorine atom becoming an ion, so fluoride. 8 endings or ite endings, those are all polyatomic naming, and you'll see that on that list. And so that kind of, you should be able to recognize if there's an 8 ending on something, then hey, that's a polyatomic. Okay, I did the difluoride thing. Okay, so let's do one with a polyatomic ion. So I can say a name. So another name for a ionic compound would be something like, why are my AirPods dying? Nope. Okay, nope, I don't want to do that one either. Let's say, nope, don't want to do that one. Okay, calcium nitrate. That's a correct name for an ionic compound. So couple things. We should recognize that 8, we have an 8 ending on our anion. So this to me indicates it's a polyatomic, right? Again, remember polyatomics, you just need to memorize. But again, you can recognize that it's polyatomic because there's an 8 ending. When there's an ide ending, then you have just monoatomic anion. So if it was nitride, like our first question we did, then it would just be N3 minus, but it's nitrate. So we should recognize that this is a polyatomic. So based upon your recall of the table, nitrate is NO3 minus. All right, so now we look to calcium, and it really, 8 versus ite is about the number of oxygens there. Again, something you just need to memorize. So calcium is just like question 21, where I said, okay, if nitrogen makes an ion, what charge is it? This is the same question you should ask yourself. When calcium makes an ion, what charge is it? Calcium is a metal. It's in group 2A. So when calcium is a cation, specifically because it's a metal, it will make the ion calcium 2+. So really, it's the same questions over and over, just kind of, organized a little bit differently here. All right, so we're not done yet. We just identified the ions that are making up this compound. The next step is to make it charge neutral. So again, just like when we did magnesium fluoride, where the cation was +2, the anion was -1, we actually need 2 of these nitrates in order for that to be charge neutral. So to build the chemical formula, when it's a polyatomic, you need to put that whole polyatomic in parentheses. So the correct chemical formula here would be calcium nitrate, where the nitrate is in parentheses, because we want to tell the reader, hey, there's 2 nitrates there making this compound. And then note here, I don't have any charges because I'm trying to communicate that this is the neutral compound. So this is the formula for calcium nitrate. So another way to think about it, it's like we have, a cation there, right? Calcium 2+, and then we have a nitrate, and that whole nitrate is a minus charge, and then another nitrate. All right, ionic compounds don't look like this, but you see we have 2 negatives and a 2+ positive. So this whole thing would be completely neutral if we kind of looked at it at 1 unit. Okay, so there we go. All right, there we go. So there's a polyatomic. All right, so let's do number 25. Again, all the same kinds of questions. The questions you should be asking yourself is, okay, if it's a metal, what is the charge, predicted charge? If it's a non-metal, what is the predicted charge? Those are the questions you should be asking yourself when putting together ionic compounds. Okay, 25. So we have a certain ionic compound. It possesses this formula. What is the group number of element X? So how I approach this question is I see, okay, aluminum, 2 aluminums and 3 X elements. So this is monoatomic again. So we kind of have to think about our, predicting charges and things like that. It's also ionic because aluminum is a metal. So if I just think about aluminum, and so if you go back to question 21 and think, okay, when aluminum is a ion, specifically a cation because it's a metal, what charge does it make? It makes aluminum 3+. That is the charge of aluminum. And so within this chemical formula, see that there's 2 aluminums and 2 of the anions. So we need to figure out what is the charge that X has to be in order for this whole unit to be neutral. And so since there's 2 aluminums, we have to consider the total charge of all of the cations there. So there's a total 6 charge. So in my mind, I'm thinking, okay, if there's +6 coming from cations, I need -6 coming from my anions. All right, a total of a -6 charge. Okay, I need to move calcium nitrate. Go away, go over there. All right, so I need a -6 charge coming from my anions. But if we think about our monoatomic anions, none of them are -6. That's a really high negative charge, but that's okay, because what we haven't considered actually is the number of anions that are there. There are actually 3 anions there. So I ask myself, okay, what charge does X have to be? How do I want to do this? What does the charge of X need to be? But there's 3 of them. So in my mind, I'm thinking, okay, if X has a -2 charge and there's 3 of them, then the total charge is -6. So that means I know that the X anion here is a -2 charge. And so oftentimes what students use to help themselves is when we have something like we had magnesium 2+ and fluorine minus, it's the charges kind of swap places and become the subscripts in the neutral compound. So there's a 1 subscript in front of magnesium, and then there's a 2 subscript in front of fluorine. So that's why when magnesium fluoride comes together, it's MgF2, because we essentially need 2 fluorines to balance that out so it's neutral. So if you kind of work backwards here, you can see that aluminum has a 3+ charge here, and that's right. So that means X needs a -2 charge. So it also works going backwards as well. And so now the issue is, okay, is X2- the answer to this question? Let's look. No, it is asking the group number. So there's just one little jump that we need to make to actually answer the question. And so we've identified the charge of your substance, specifically of your anion. And so now we need to kind of think backwards and think, okay, what group element typically produces a -2 charge? So if we recall the equation that your anion charge equals your group -8, we would see that it's actually group 6A that typically make 2- anions. And so this question is very much like the previous questions we did, but it's working a little bit backwards, where we're given an unknown element, and we have to go back and figure out, okay, what group number does it belong in based upon its charge and it's in the compound. While in all the other questions, I gave you the identity of the element, you can figure out what group number they are, their charges, and then make the neutral compound. So we're working backwards a little bit, but it's all the same concepts. So if you have those concepts down, then these questions will come together, and it really just comes with practice. Okay, so let's keep going. Okay, naming, that's what we are here for. So the big idea with naming, we only really learned 2 different types of naming rules: ionic and molecular, right? And so with naming, we have different rules for ionic and molecular. So I will reiterate, with ionic, you never, ever, ever have to tell me how many of each ion there are, because it can always be predicted by their charges. But with molecular, you do need to use those prefixes, because in molecular compounds, there are no charges. So you have to tell the reader exactly how many of each atom there are. So that's the first thing you should think about when looking at a substance, is think, okay, is it ionic or is it molecular? And so again, kind of at the beginning, we were able to identify whether something was ionic or molecular based upon its composition. It's ionic if there's a metal and a non-metal. but it's molecular when there's all nonmetals. And so based upon that, those are the naming rules that we go under. And so for ionic compounds, it's really just name the cation, then name the anion with the appropriate ending. I will note that with some of your cations, sometimes there is a fixed charge cation, meaning that it's essentially a main group element where you can predict the charge, so you don't have to use Roman numerals. The other type of ionic compound is when you don't know, you can't predict the charge, and I call those variable charge cations. And with those, you need to use Roman numerals in order to tell the reader what the charge of the cation is. And once you tell the person reading it what the charge of the cation is, then they in their mind can build what the chemical formula is based upon the charge of the cation, which you told them using a Roman numeral, and the charge that you can predict from the cation. So Roman numeral. Okay, so this is what should go on our mind. The first thing is it ionic or is it molecular? Right, so this first one, BrCl. So I just look at the composition and I see that Br and Cl are both nonmetals, right? Both nonmetals, so this is molecular. So that means I use molecular naming rules. So I have to tell the reader what the number of atoms of each element there are. And so there's one bromine, one chlorine. So by convention, if there's one of the first element, you don't have to put mono, only if there's one of the second element. And I'll show you a trick to help me memorize it. So this name would be bromine, mono, chloride. So whatever the second element gets, whatever the second element is, it gets the "ide" ending, similar to ionic, but it's not ionic. All right, so keep that in mind, that even though it's chloride is what like an ionic name like sodium chloride would be, it is not ionic. It just has that same ending there. All right, so the like if I was trying to trip you up or something, one of the options would be something like monobromine, monochloride. But again, if the first element in a molecular compound, there's just one of them, you drop the mono. But if there's two of that element, then you do have to put the prefix like di or tri, whatever it is, to indicate how many atoms there are. I like to think of CO2. I feel like most people know that this is called carbon dioxide. All right, so carbon dioxide. So in this example, also molecular because it's all nonmetals. But in this example, carbon, it also has just one carbon is the first element. And so when you think of the name carbon dioxide, we don't say monocarbon dioxide. That just sounds weird. We just call it carbon dioxide, and that's the correct name, because when it's the first element is one, you don't need the mono. But I think one of the back exams had something like F2O3. So in this example, F2O3 you do have to use the prefix for the first one because it's not mono. So this would be difluorine trioxide. So note here, all of the second elements get that "ide" ending, and they always get a prefix no matter how many there are. So another example, CO, so like the poisonous gas, this is carbon monoxide. All right, so with molecular naming, so note here, C and O, they're both nonmetals. So if you tried to use, let's say, ionic naming rules, so both CO2 and CO would have the same name. So again, it's very important that you identify first the composition of the substance. Does it fall under ionic or molecular naming? All right, so in this case, we have to tell the reader how many of the second element there is. Okay, so let's keep naming. All right, so the next one, CaC2H H3O2. So we should be able to recognize that this substance, the C2H3O2, this is a polyatomic that you should have had memorized. And so this substance is called acetate. All right. So since it's acetate ion specifically, it's a polyatomic ion, this has to be ionic because there are ions present. So I think ionic naming is a little bit more not difficult, but recognize that. Remember, with these ionic substances, you just have to name the cation and the anion. You don't have to indicate the charge. So simply, this substance would be called calcium acetate. So hopefully you can recognize that C2H3O2 is acetate and calcium is the cation. And so we just say the metal and then the non-metal, or sorry, the cation name and then the anion name. So this is just called calcium acetate. So also keep in mind within our ionic naming rules, I said within those namings, identify if the cation is a fixed charge cation, meaning that you can predict the charge. Calcium is one of the ions that we can predict its charge. Calcium is always a 2+ cation. And if you inspect the formula, it does become a charge neutral substance because acetate is a minus charge and there's 2 of them, and calcium is a 2+, so it's all charge neutral. So that's different for the next substance. So this substance, TiSO4, 2 of them, is also an ionic substance. And how I recognize that is, one, titanium's a metal and SO4 is a polyatomic anion. So I know that sulfate, SO4, is a 2- charge. So for ionic naming, it is simply just you name the cation, then the anion. But if the cation is a charge that you can't predict. So if we look at, see where titanium is on the periodic table, it's a transition metal. So we can't predict the charge like we can for magnesium or calcium. So we have to tell the reader what the charge of titanium is. So we have to figure that out first. So sulfate is there. We know the charge of sulfate. So we can figure out, okay, what does the charge of titanium need to be in order to be charge neutral? And so since there's sulfate is 2- and there's 2 of them, so there's 2 of them, there's a total 4- charge coming from the anions. So that means titanium needs to be a +4. And so this determining the charge of titanium is necessary because we have to use Roman numerals in order to name this. So it still will be just name the cation, name the anion, but because titanium is a variable charge, we need to use the stock system, Roman numerals, to tell what the charge is. So titanium 4, so Roman numeral 4, and then sulfate. That's it. Okay. Is the exam multiple choice? Yes. Ti is not thallium. All right, so let's keep going. How do you know if polyatomics are metals? Polyatomic ions are ions. So polyatomics, you don't think, are they metals or non-metals? Polyatomic ions are always ions. So that was how I knew that these 2 substances were ionic, because if there's a polyatomic in there, then it's an ion. So it has to be ionic. So the question is, do you have to identify polyatomics as a metal or non-metal? You don't. The identity of the polyatomic is the ion charge, if that makes sense. Do you know where that chart is? I don't know what chart you're referring to. Will spelling count on the midterm? Hey, make sure when you're asking questions to bring it up on the question thing. Will spelling count? So part of your studies was memorizing the names and symbols of some of the elements, and that includes how to spell them. Where is the chart? So yeah, Ti is not thallium. So look again at your study guide for your periodic table naming. Yes, the exam is multiple choice. There are some small number inputs. It's very similar to the practice midterms that you see that I have posted. They're very similar. Okay, so let's keep going. So the next one, zinc oxide. So again, I recognize it's ionic because there's a metal and a non-metal. Okay, if there's a metal present, then it basically has to be ionic because metals are only in ionic substances. Molecular compounds only have nonmetals within them. All right, and so zinc is looks like it's one of our variable charge metals because it's in your transition metal block. But if you look at the slides concerning transition metals and variable charge cations, zinc was an exception. Zinc, when it is a cation, is always zinc 2+. Always. And so that is one of the slides within monoatomic cations naming. And so since zinc is a fixed charge cation that we can predict the charge based upon its identity, it's always a 2+ cation, we just call this zinc oxide. All right, so zinc oxide, it's one of those sunscreens that lifeguards wear on their nose. That's zinc oxide. Okay. All right, so the next one. So hope you can recognize that also this is ionic because Ag is a metal, Ag is silver, and nitrate is a polyatomic ion. So since there's an ion present, it has to be ionic, ionic. And so within here, when you look at ionic substances, again, think to yourself, is it fixed charged or variable charge? Silver is, again, another one of our exceptions. It's on that chart, that yellow chart that I have. Silver, when it's a cation, is always Ag+, always, even though it's in the transition metal block, like the transition metals within there. But Ag is always Ag+. And NO3 is nitrate, one of our polyatomics. So this would just be called silver nitrate. We don't need to use the stock system because we can predict the charge of silver. Okay, next, AuBr. So Au, gold, is right under silver. All right, gold is not a substance, a cation that you can predict its charge. So this is another ionic because Au is a metal. So in this example, we do have to use the stock system because we don't know what, so gold can be a multitude of charges. It can be +1, it can be +3. So we have to tell the reader what the charges are. You don't have to memorize it. You can determine this charge of this gold atom or this gold ion based upon what it's attached to. So if we think about what it's attached to, bromine, just like how we did our titanium one, how to figure out the charge of the cation, Br is always a minus charge. And so that means Au has to be a plus charge in order for that to be neutral. So this would be called gold 1 because it's a +1 charge bromide. Not all transition metals are variable. Yes, that is correct. There's a slide, it has like a periodic table with like yellow highlighting. All of those metals, some of them also aren't transition metals. So most of the transition metals are variable, and some of the metals to the right of the periodic table are variable charge, except silver, zinc, and aluminum. Those are the three that are kind of in that same area, but they always have a fixed charge, and it's on that slide, the three exceptions there. Everything else would be not. Why wouldn't nitrogen be nitrate? So NO3 is a polyatomic that you need to memorize. So NO3 minus it's a polyatomic that you need to memorize. That's a polyatomic. So that whole unit is charged. And so trinitrate is also molecular naming rules, but this is an ionic compound, so it doesn't fall under that. Why do some end in 8 and others "ide"? So when it is a monoatomic, it ends in "ide" based upon the naming rules from the lecture slides. If it ends in 8, then that's a polyatomic ion that you need to memorize. Okay, someone raised their hand. Why isn't it bromine instead of bromide? Because bromine means Br neutral atom, that there is no charge. But once it becomes a negatively charged substance, Br minus, that is an ion, specifically an anion. So we have to call this bromide. All right, so just Br neutral, or if we are talking about like the element bromine, like Br2, bromine in its elemental state is a diatomic, we would call this bromine. But because in this ionic substance, Br minus is a negative charge, we call it bromide. And it still follows the same monoatomic naming rules within there. Okay, I think I got all the questions. So I'm gonna do that. Okay, what's the next question? Oh, more names. Okay, more names. Okay, so within these names, it's the same thing. We have to identify, is it ionic? Is it molecular? And we follow the rules within those. So, so the names there, we look at these names and I identify, there's a couple ways you can do it. Either look for the molecular naming rules. So in here, I see tetra. Tetra is only used in molecular naming. You'll never, ever see it in ionic naming, ever. So this has to be a molecular substance. Also, you can see that sulfur and fluorine are both nonmetals. So since this is all composed of nonmetals, this would be a molecular naming, molecular. All right. So within there, these molecular naming rules, now we have to work backwards. So what's nice about molecular, remember the name tells you exactly how many atoms there are. So sulfur, it's not monosulfur, remember. So if it just says one element at the beginning, for molecular only, you just write one atom within there. And then tetrafluoride. So fluoride means fluorine here, so F, and it tells you the name because the prefix that it's attached to tells you how many there are. So this is SF4. Okay. All right. So next one, ammonium phosphate. So this one's a little bit tricky. All right. So ammonium phosphate. So again, memorizing those polyatomic ions, we should be able to recognize, okay, ammonium, when we memorize that polyatomic, that is always NH4 plus with a plus charge. So remember, with polyatomic ions and memorizing those, you need to know the formula and the charge and the name for those. And so phosphate is also a polyatomic ion. And because this substance is made of ions, this is ionic naming rule. So remember, always forming neutral compounds is important here. So NH4 plus is the cation. Phosphate off of the chart is PO4 3 minus within there. All right. So now, kind of like when we were building ionic compounds before, we need to think, okay, how can we combine these two substances to make a neutral substance overall? So that would be, I would actually need 3 of those ammoniums, the 3 of the cations, in order for it to be charge neutral. So NH4, all right, so that's my cation. I need to indicate that there's 3 of them there to balance out the -3 charge in phosphate. And so this would be NH4, 3 of them, PO4. So that would be the correct name, or sorry, correct formula there. And so this one's a little bit tricky because, you know, I told you that all, ionic compounds start with a metal, but in this example, it doesn't. And that's the reasoning is because both of the components are polyatomic ions. When we combine ions, we make ionic compounds. And so since both of them are ions, we still use ionic naming rules within here. So this one's kind of like a special one where everything is actually a non-metal technically, but it is an ionic substance within there. Okay, so yttrium sulfide. All right, so ionic naming, it's all about when you identify that it's ionic, when you're going from a name to a formula, it can be tricky because you need to figure out what is the charges of everything. But the nice thing about the stock system is that it tells you what the charge is when you see those Roman numerals. So yttrium, you don't even have to think about it. Yttrium, Y on the periodic table, it says it's Y with a 3. The 3 Roman numeral tells us it's a +3 charge. So this would be yttrium 3 plus. Sulfide, ide means monoatomic, monoatomic sulfur. So we need to ask ourselves, what's the charge? So S2 minus. there, and then you combine them, so it is a charge neutral substance. So this would be Y3, sorry, no, Y2, S3. Yes, okay. All right, so keep going. I need to go faster. We've already gone at like an hour. Okay, what's this? Whatever. All right, so the next one, lithium sulfate. So I recognize lithium as a metal. So this is ionic naming. Sulfate is a polyatomic we need to memorize. So SO4, 2 minus. Sulfate, 8, indicates it is a polyatomic. Ide means that it is a monoatomic. So I actually kind of showcase that with these two being right next to each other. Sulfide is different than sulfate. 8 indicates a polyatomic. The ide ending indicates a monoatomic anion where you can predict the charges. Sulfate, the 2 minus, is just a charge you need to memorize. So looking at the metal here, lithium is group 1A. So lithium is a plus cation. So putting that together to be charge neutral, Li2SO4. Okay. So yeah, putting these two next to each other, I think I did it on purpose. Sulfide versus sulfate. Okay, let's keep going. All right, chromium 6 oxide. Okay, so chromium metal. So this is an ionic. Well, how did you know the charge of Y? So when the stock system is used, remember, you're telling the reader what the charge is, because yttrium is a transition metal, so you can't actually predict it, that you have to be told what the charge is. So in this case, yttrium 3, I am trying to tell you that yttrium is a 3+ cation. I love the stock system because you don't have to think about the charge of the cation. It tells you it right away. So just like when we are going backwards, going from like titanium sulfate, or sorry, titanium 4 sulfate or gold 1 bromide, we had to tell the reader what the charge is. We can use those charges when building our neutral compound going forward. So this substance, chromium, is a 6+ cation because it's +6, and then oxide is O2 minus. Ide is monoatomic. We can predict the charge of oxygen when it's an anion, -2. So then putting that together to make a neutral compound, CrO3. All right, okay, let's keep going. Magnesium nitrate, ooh, another ionic compound because magnesium is a metal. Magnesium is group 2A, so magnesium 2+. Remember, guys, I'm not memorizing these. I'm just looking off the periodic table where a lot of these metals are. Nitrate is one of the polyatomics you need to know, so or need to memorize, NO3 minus. All right, and then you just put that together to make a charge neutral compound. So MgNO3, 2 of them. Okay, so I did that one. All right, done. Okay. All right, so we did a lot of ionics in a row, and the main thing is there are a lot of metals. They start with a metal or some type of, they have ions within them. And so this last one finally is a molecular naming. There's a couple ways I can tell. I see the tetra and deca prefixes. You only use those prefixes in molecular because you can't predict charges. You have to tell me exactly how many atoms there are because there's nothing to predict. And so the other way you can kind of identify its molecular is that phosphorus and oxygen are both nonmetals. So there's only nonmetals there, so it has to be molecular. So tetra means 4. So there's 4 phosphoruses, and deca means 10. And so that's attached to oxygen. Oxide is oxygen there, and so there's 10. So P4O10. So there is naming. So if naming was tough for you, I really suggest going back to, especially the ionic compounds, because I think they're much harder. Going back to this first page, thinking about, what's going on, predicting the charges, where they are on the periodic table. Why isn't it P2O5? Because tetra means 4 and deca means 10. So we write it P4O10. So if I wanted to say P2O5, that would be diphosphorus. So if you Google P4O10, I think Google will tell you that it's P2O5, right? But these exams aren't you don't have access to the internet, so using the naming rules that we learned in class is going to help you forward. So P2O5 would be diphosphorus pentaoxide or pentoxide. It'd probably be pentoxide. Pentoxide. So remember, it's the prefixes that tell you how many is there. Why is it not C2O3? Because C2O3 would indicate that it is chromium 3+. But in this example, chromium is a 6+ cation. So we ask ourselves, how many anions do we need to balance that? And so again, I think if you Google chromium oxide and you don't indicate the charge, Cr2O3 will come up. But that is actually chromium 3 oxide. I'm talking about chromium 6 oxide, which is a different substance. All right. Is this midterm? So the midterm is very similar to the practice midterm that you see on Carmen. So there's, most of them are multiple choice, but there are some small input a number type of question. All right. So I'm gonna put those. Okay. All right. So do we want to do Lewis structures, or do we want to go back to chapter 1? Can you write it up in the chat what we want to do? Oh, so we have an hour. Okay, let's go back to chapter 1. Very good. Okay. So now I actually need my calculator. Okay. So let's think about significant figures. So remember, with significant figures, there's 2 sets of rules: addition rules and multiplication division rules. They're completely different. Do not mix them up. So what we see here in this question, the correct number of significant figures in this operation, there's actually 2 things that I'm kind of showcasing here. One, it's scientific notation. So these 2 numbers are in scientific notation. This is not like a multiplication. I mean, it is a multiplication type of thing here, but we don't have to consider multiplication rules with these individual scientific notations. What's important here is the subtraction, that we have to follow subtraction or addition subtraction rules, where we look at the place value of the place values that are shared between the 2 numbers that you were subtracting from one another. So within subtraction, we need to make sure that we line up all the place values. So it'll probably be easiest if we convert both of these numbers to their standard form. I can't really add these in and really inspect their place values when they are shown in scientific notation. So it's best to undo them first. So so I like to think, okay, 5 point whatever times 10 to the 2. This is a big number because it's times 10 to the 10 squared, which is a big number. So I'm going to move that decimal place over 2 places and then rewrite the number. So this number is 586.39. And I'm subtracting it from this value. So it's times 10 to the -1. So that indicates it's a small number. So I'm going to move that decimal place over to make it a smaller number. So this number is 0.6115. All right, so there's the subtraction. So remember, with subtraction, it's not about counting sig figs. It's about what place values do the 2 digits share. So I like to go to 3rd grade and line up the digits so all the place values match up, so that we're matching up the decimal places, and then we're subtracting them. And so what I like to do, okay, so I didn't line this up very good. So this should be 1, 1, 5, right? Okay, so I like to look at these values and think, okay, the first number is known out to the 2nd decimal place, right? The number that we're subtracting from it, also known out to the 2nd decimal place, but it goes further. We're looking for the place values that the 2 digits share. So that means our answer can only go out to the second decimal place. That's what that means. So it's all about looking at the place values here, that both values share the second decimal place. So we know our answer out to the second decimal place. Or you can think about it. So these trailing numbers at the end here, yes, we're subtracting them from zeros, but those zeros aren't really known. We don't actually know what numbers are beyond this first value. So when we get numbers out here, we don't actually know the true, we don't have certainty in the digits past the second decimal place because it's the second decimal place where that's the last place, the rightmost place where both of the values have shared sig figs. And so just put that whole operation into your calculator. And so if you put it in your calculator, you get 585.7785. All right. And so again, we're inspecting place values here. So that means we will round when we report our number, we're going to round to the second decimal place within there. All right. So the true value here with rounding rules. So we're going to actually round that 7 up because the next value, even though it's not significant, is telling us, okay, round up. So the true number here would be 585.78. So that is the answer. So it has 5 sig figs here. But remember, it's all about the place value. And I think all of these answers are denoting it in scientific notation. So we have to then convert it back to scientific notation to make sure that we are reporting it correctly. So 585 is a big number. So I have to move that decimal place over twice. And so to make a big number, I will do times 10 to the +2 because I move the decimal place over. Yes, the key will be posted when I post the recording to this. And it's an actual key. I have a key. So I won't post this. I will post the actual key. And then you write the number, making sure that you show all of the significant digits in scientific notation. So 5.8578 times 10 to the 2 would be our answer. So whichever one that is. It's this one, I guess. I think it's that one. All right. Okay. So addition, subtraction, different than multiplication, division. All right. So let's do another one. Ooh, more of them. So we have combined operations here, addition and subtraction and multiplication. So my strategy here is just like you would put this in your calculator. You would put this parentheses in your calculator first, get the answer. You would put this in your calculator, get the answer, and then you multiply them together. So it's the same idea here. We will do this operation first, figure out, okay, what is the answer to the correct number of significant digits? What is the answer to this to the correct number of significant digits, and then multiply them together based upon the answers of these two individual values. So we have to do two addition, subtraction. So again, let's go to 3rd grade and put those numbers on top of one another. So 341.70. All of those numbers are significant. That 0 is significant. This number is known out to the second decimal place. And so 21.1. So we're adding those two numbers. So just like in the previous question, we ask ourselves, what digits, what place value do the two numbers share? Right. So if I think about it, okay, all of these numbers are known. Come on. All right, all of these numbers are known, and then 22.1 is only known out to the first decimal place. So that means when we get our answer, we can only know it out to the first decimal place because both the numbers share that first decimal place. I don't know the second decimal place in that second number, so I can't know it in the answer. And so if you just stick that number in your calculator, you get 363.80. All right, but this number, if we were done, you would just report 363.8. And so just keeping in mind, this has four sig figs because we'll need that information for the next step, right? So that's addition. So let's do this one, subtraction now. So it's the same idea. We need to look at the place values. So we need to stick the numbers on top of one another, 0, 8, 2. All right, so just by inspection, looking at those two values, they are both known out to the third decimal place, that they both have significant digits in the third decimal place. So that means our answer will be known to the third decimal place, right? So this will be our last digit that we know. And so when you stick that in your calculator, you get 0.74. That's what your calculator says. But remember, we know out to the third decimal place. So calculators are dumb. We have to apply our knowledge of significant figures. So we actually have to put that zero in there, even though our calculator says 0.74. But we know that this answer is known out to the third decimal place. So we have to put that zero there. And that's important here because that gives that number 3 sig figs. Because our next operation is now just multiplying the two numbers together. So we're going to be multiplying, so I'll just rewrite it. So 363.8, which has 4 sig figs, times 0.740. That 0 is significant. This has 3 sig figs. This one has 4 sig figs. So now when it's just multiplication division, it's quite straightforward. You just you look at all the numbers individually. Your answer gets rounded to whichever is the smallest number of significant digits. So if you stick that in your calculator, you get 269.21. All right, so I just wrote a bunch of digits. So we look at that number and think, okay, how can I rewrite this number so it has 3 significant digits? I will keep the 2, 6, and the 9. So this number, this answer will be 269. 269. All right, 269. If you downloaded this this activity like over the weekend, yours might be a little bit different because I realized I didn't have some right answers in these. I thought you have to wait till the end to round. We're at the end. This is at the end. So 269.21. So I just left a couple digits so I could show you how to round. All right. And so 0.740 is 3 sig figs. So our answer needs to have 3 sig figs as well, not 4, because 3 is smaller than 4. All right. And so within here, yes, it is always true that you never want to round to the end. So what is kind of nice here is that the number here at the end is a 0, but pretend that number wasn't a 0. Let's pretend it was like a 4 or something. Still, that 4 is not significant, but I would, if this was me, I would continue on with that 4 into the next calculation, but understand that the last significant digit is the 8, and so it has 4 sig figs. And that's often why I will underline numbers if I'm mid calculation and I just keep some extra digits so I don't lose any precision within my answer, or sorry, no, it'd be accuracy within my answer. All right, and so there we go. So it's not this number because that's 4 sig figs. Okay, awesome. All right, let's keep going. So what are the chemical symbols for silver, copper, lead, and tin? Okay, so this is just knowing the periodic table. And so these are kind of the tricky ones. Silver is Ag. Copper is Cu versus Co, that is cobalt. All right, so I feel like if you were to get copper wrong, you would say CO. Lead is Pb and tin is Sn. All right, and so if you were looking at that word thinking tin, you might think it's Ti, but nope, that's titanium. Titanium. And I think the question before was they thought Ti was thallium. Thallium is Tl. I'm pretty sure. Thallium is, yeah, it's element 81. And titanium is element 22. 22. Thallium is element 81. Yeah, okay. Yeah. So if you were to mix up these element names. So then I think our correct answer is, I think it's the last one. Is it the last one? Yeah, it's the last one. So you can see here, these are the common I guess misconceptions for some of the elements. You know, I'm trying to trick you up. Ag is silver, but I also have Au here. That is gold. I have the cobalt and the copper. So copper is Cu, not Co. Lead is Pb. And so I just have, I don't even think Ld is a element. I don't think it is. So lead is one of our weird ones. And then tin, I have Ti here because you might think that's tin, but nope, that's titanium. Tn, I don't think it exists. Pb, that's lead again. And so Sn, that's tin within there. So I think actually what would be a harder question if it was the other way. If I would have given you the symbols and asked for the names correctly, I think that would be a better multiple choice question, because it definitely forces you to look at the details within there. All right, so that's the periodic table stuff. And yes, knowing how to spell them is important, because if it was the other way, if I would have given you the element symbols, you know, I can put different element spellings in there or something to trip you up, like fluorine. Fluorine. All right, I need to make sure that that's right. It's Fluorin. So I might write something like flowering, because I think at first glance, you might think that that's right, but it's not right. It's not flower. That's how I memorize it. Fluorine is not flower. So it's U before O within fluorine. Okay, so those are the elements. So let's do some dimensional analysis now. So we have the density of aluminum, and it's asking what is the mass of in kilograms of a 12-inch cube of aluminum. So recognize that this value given, 2.70 grams per centimeter cubed, when you're given units like this where there's a fraction in it, you can make a conversion factor or an equality that helps you relate to values. So what density tells you is the ratio between mass of a sample and its volume. So we can rewrite this number. So whatever unit is in the denominator gets an implied 1. So this means that 2.70 grams of aluminum is equal to 1 centimeter cubed of aluminum, where the bottom unit, the denominator unit, gets that implied 1. So this allows us to relate the volume of a substance to its mass, which is useful because they give us kind of the volume. They give us that we have a cube. We have a cube and each side is 12 inches. 12 inches. So in order to get the volume, you take the length cubed, right? But if we take 12 inches cubed, we get the unit of inch cubed. Inch cubed doesn't match the density unit that I have. So we need to kind of play around with the units in order to get the volume into a unit that's useful to us. So the best thing, yes, yes, the recording will be posted. It's on the page that you clicked on. It says that the recording and the key will be posted right on that page after we're done. So the inch, we're in the unit of inch cubed right now. If we were to take 12 cubed, 12 inches cubed would give us the volume in inch cubed, but we don't want that. We need it in centimeters cubed because that is what our density unit is in. So the best way to kind of get around that is let's change this this length unit into centimeters first before we cube it. And so that's good because I give you the relationship between inch and centimeter. So let's change that length into centimeters first. So the one length of our cube, and remember, it's like 12 inches on each side, right? So 12 inches 3 times. So the length, 12 inches, let's convert that into centimeters. So taking that conversion that was given, that 1 inch equals 2.54 centimeters. All right. So here's another conversion. This one you're given, and it's on the supplemental information sheet that you have access to already. So within here, looking at this equality, you need to match units to get those units to cancel. So we're currently in the unit of inch. So I'm going to put 1 inch on the bottom. And then I have to put the other guy up top. And that's good because I want the unit of centimeters. So if you look at how the units cancel, inches cancel, and we're left with centimeters. And so if you do that math within there, you get that the one length of your cube is actually 30.48 centimeters. All right, and so here's an example where I would not round just yet. So I would just keep that whole thing and recognize that 30. If I would have rounded, it would just be 2 sig figs, but I'm not going to round just yet because we're not done. So this is the length in centimeters. So I need to get the volume now in centimeters cubed. And so I just take that number. So volume, remember, is equal to length cubed. I don't want it in inches cubed, so I'm going to do centimeters instead. So 30.48 2 sig figs, centimeters, cube it. And so that means, you know, you get the answer, the unit you get out because we're cubing it will be centimeters cubed. And that's good because the density we were given is in centimeters cubed. And so you get that answer. It's a big number, 28317 centimeters cubed. And again, I'm just not going to round because I don't like to, I feel like I'm like shorting change or something. I guess that's like the best analogy I have. I don't want to short change until I'm at the very end. So if I was done, I would have rounded to 2 sig figs, but I'm not done. So this is my volume. So it's this number is useful to us because now we have our volume of our cube. So we had to do a little bit of stuff to it in order to get it into centimeters cubed. But now I can use density to relate a volume measurement to a mass measurement, right? And so just like the equality we did before for inches and centimeters, I want to match up the units. So 1 centimeter cubed is going to go on the bottom, and then the 2.7 grams is going to go up top. All right. And so this will give me the mass of my cube in grams. But let's just recall what the question is asking. It's asking for the mass in kilograms. So we need one more step here, because if we finished, this would give us the gram measurement. So the last step is to convert grams to kilograms. So the prefix that you need to memorize is a kilogram or kilo of anything is 1,000 of the base unit. So the equality here is 1 kilogram equals 1,000 grams. And just like all equalities, you know, I don't have to think, do I need to multiply or divide by 1,000 to convert to kilograms? The equality tells you, and as long as you cancel out the units, then you'll be doing the correct thing. So right now we're in the unit of grams. So I want to put the 1,000 grams on the bottom, so the gram unit cancels. So that leaves me with the kilogram unit left over. And I'll just show you those units canceling. There we go. And so then that's all you would put in your calculator. The 28,000 number times 2.7 divided by 1,000 would give you your answer. And so remember, this is 2 sig figs. So density has 3 sig figs, but 2 overrides that. And then the 1 kilogram is 1,000 gram. This is infinite sig figs. Those don't have 1 sig fig. It's their exact numbers. And so our answer here is 76 kilograms. All right. And so there is our answer. And you see here, A, that would be if you left it in grams. Right. So I have that. So make sure that you look at the question there. Okay. So let's keep going. All right. The boiling point of ethanol is 78 Celsius. What is the equivalent temperature in Kelvin? So for those of you out there, I hope that you've looked at the supplemental packet that you will be given. Can you do scientific notation and get the same answer? I don't know what you mean. You mean report 76 in scientific notation? Like if you reported 7.6 times 10 to the 1? Is that what you're saying? Why is it 2 sig figs? It's 2 sig figs because 12 inches. This number came from 12 inches and I kept saying it's to the conversion. Oh yeah, if you do the conversion 1 times 10 to the 3 grams is 1 kilo, yeah, you'll get the same thing. As long as you're putting in scientific notation in your calculator correctly. I urge you guys to actually put in the numbers in your calculator, because when you're there, like, you are doing the work. When we're in class, I know that I'm moving really, really fast and I just give you the answers, but just make sure that you are putting these numbers in your calculator. Because we work with some really big and really small numbers. So it's important here. All right. It's 2 sig figs because the number here, 12 inches, has 2 sig figs. And all of this was multiplication. Okay. Is that it? Is that it? Okay. So, so for those of you out there, do you have to memorize the temperature conversions between Fahrenheit, Celsius, and Kelvin? Do you have to memorize it? No, good. That means that you guys looked at the supplemental packet, the scratch paper sheet or whatever, because you are given your Celsius, Fahrenheit, Kelvin conversions. There is no conversion between Fahrenheit and Kelvin because you can always go through Celsius. So the idea here is that Fahrenheit, you can always get Celsius from there, and Celsius is always directly related to Kelvin. All right. So if you're given Fahrenheit and need to go to Kelvin, you just have to do two different calculations. So there's two different equations, so just know how to use them. So we need to go from Celsius to Kelvin, and so that I don't like pink. That equation is the temperature in Kelvin equals your Celsius temperature plus 273.15 Kelvin. So this is just addition rules, all right? So we're just adding these two numbers. So 78 plus 273.15. So just looking at this, this is addition, right? To what place value do we round our answer to based upon this? Throw it up in the chat. What place value do we round to our answer based upon how these numbers are written? It's addition. Can we throw the ones place? Yes, because we know out to the ones place in our the Celsius temperature. We know a lot more digits in the Kelvin, but that doesn't matter because we are limited by whatever place, you know, is limiting us. So in this case, it's the ones place. And so whatever that added, and it's to the ones place. What is the answer? What's the answer? I don't feel like putting in my calculator. It is 351 point something, but it doesn't matter because what we report is 351 Kelvin. All right, so is that answer there? Yes, thank goodness. All right, so there we go. All right, so next question. The specific heat of aluminum is 0.215 calories gram per degree Celsius. If 320 calories are required to heat a sample of aluminum from this temperature to this temperature, what is the mass of the sample of aluminum? So we're thinking about specific heats. So there's a specific equation that we use. We use Q equals MCAT. That's what I like to call it. Do we need to memorize this equation? Yes or no? Do we know? No, we don't. It's on the sheet. You know what I should have done? I should have told you, bring your periodic table, bring your calculator, and print out that supplement, the scratch paper sheet, so you know exactly what you need. Actually, that's my tip for you. If you're doing practice exams under like a timed type of constraint where you're trying to, you know, meter yourself, make sure you have that supplemental packet with you. All right, so we're using Q equals MCAT here because we're talking about specific heat. But there is one equation that I did not give you. It's I don't think I did. What delta T means. If we recall what delta T means, it's the change in temperature of your sample. So I give you how much the sample changes, but it's specific how we calculate it. It's always the final temperature minus the initial temperature. That's the value we put in. Yes, TF minus TI. Very good. Is that given? Is delta T given in this sheet? Yes or no? No, it's not. Okay, so you do have to memorize this. All right, so really this question is kind of just plug and chug. Think about what's given and what we're trying to calculate. We are given the specific heat. Boom, CS. We are given the heat in calories, which is good because our specific heat is also in calories. So then there's no conversions we need to do. So the units match there. So a student pointed out, I think very astutely, that sometimes I give energy units in joules. And the specific heat is in joules, and that's fine using those numbers because joules will cancel with each other. In this example, it's both in calories, and that's fine too. They both will cancel with each other. We don't have to convert anything. Okay, so we have CS, and we have how much the sample changes. So that's delta T. So we have everything we need, and it looks like we are calculating the mass. So really, it's just plug and chug now. But before I put that into the equation, I always like to just calculate delta T. So right here, our sample is going from 15 to 80 degrees. So it's increasing in temperature. So remember, it's TF minus T initial. It was initially at 15 degrees, then its final temperature was 80 degrees. So delta T is 65.0 degrees Celsius. So that has 3 sig figs there. All right. Okay, and now it's just plug and chug. So let's put in all those numbers. So Q, so I'll put that here. Q is 320 calories equals, so this only has 2 sig figs. So it looks like my answer is going to have 2 sig figs. So I don't think these numbers communicate that, but that's okay. We'll choose the closest one. So that's Q, 320. M, that's what we're calculating. Specific heat right here, it was given, it's 0.215 calories per gram degrees Celsius. And then finally, delta T, which is positive 65 degrees Celsius. And you'll see all those units cancel out. So once you just calculate for M, so it's just, so take 320 divided by 0.215 divided by 65, we get that M. The mass of the sample that raised that temperature given that much heat is 22.89 grams. So if this was a numerical input, typically how those questions are is I tell you what place value to submit an answer. So this would be a good question for a numerical input. It would say, okay, what is the mass of the sample? Report your answer in grams to the first decimal place. And so you would put into Carmen, into the box, you would put something like 22.9, and you would not put the unit. So I'm very clear in the directions in that way. But this question is a multiple choice question. So D's our answer. Okay, so, but really it should be 2 sig figs. Sorry. Okay, it should be 23, but that's okay. That's okay, since it's just all multiple choice here. Okay. So let's keep going. So let's consider the balancing the chemical equation for the combustion of ethanol. So I give you the substance here. So this is one of our reactants. So in combustion, we always react oxygen, and the products for combustion are always CO2 and water. So here is the balanced not balance, but the skeleton reaction for a combustion reaction. So if I said, okay, you're combusting heptane, and I give you the chemical formula, all you're doing is changing the first substance here. The rest of the parts of the of a combustion reaction are exactly the same. We're reacting it with O2 because you need oxygen to feed a fire, and the products are CO2 and water. So I have a very systematic way that I balance chemical equations. I've written it in almost all of my keys for anything, recitation, all that. So I'm not going to really rewrite the details here. The balancing activity sheet that I have for chapter 1 also has the very detailed systematic way I balance chemical equations, but balance combustion reactions. I'm getting tired. But just to kind of summarize it, you always balance your carbons first using CO2. You balance your hydrogens next using water, and you always balance your oxygens last. Okay. That's basically the main point. And so I'll just show you how I do it. So the first step is you balance your carbons using CO2. So I look at the thing I'm burning because that's the only source of carbon. And I make sure that the coefficient balances the number of carbons. So I'm just going to put a 2 in front of CO2. So there's 2 carbons on each side. Next, you always balance the hydrogens. So be very careful here. The hydrogens in the thing we're combusting, see how there's hydrogens are kind of in multiple places. So there's actually a total of 8 hydrogens total there. So keep that in mind. It's not 7 hydrogens, it's a total of 8. So since there's 8 hydrogens on the reactant side, I need to make sure there's 8 hydrogens on the product side. Water, H2O is the only source of hydrogen. So I'm going to put a 4 in front of water. And the reason I put a 4 is because there's 2 hydrogens per water molecule. So there are a total of 8 there. And so this last step, balance O2 last. And so the thing is here is what I like to do is take inventory of all of the oxygens on your product side, and then just adjust the coefficient in front of oxygen so they match. Because we're done balancing this side. We have coefficients. I don't want to change them anymore. So if I kind of just count all of the oxygens there are 4 oxygens coming from CO2 because there's 2 CO2s, there's 2 oxygens each. So there's 4 oxygens coming from there. If we look at water, there's also 4 oxygens coming from there. So there's a total of 8 oxygens on our product side. So my goal is to make sure that there is a total of 8 oxygens on the reactant side as well. So let's see how we can get that. how I want to make sure that they're the same number of oxygens on each side is only by changing the coefficient in front of O2. But we need to be super cognizant here because look, there's an oxygen right there in the thing we're burning. So I like to think, okay, I need a total of 8. There's 1 oxygen coming from my thing that I'm burning. And I think to myself, okay, how many oxygens from O2 do I need to make it 8? So in order for there to be 8 on the reactant side, there needs to be 7 oxygens coming from O2. But recognize that the subscript there's 2 oxygens per oxygen molecule. So you really actually need not 7 O2s, but you actually need 7 halves O2 or 3.5. You can think of that. If you have 3.5 O2s where each molecule gives you 2 oxygens, that would give you 7 oxygens total. So this reaction is balanced. It's balanced. You can count it. It's balanced, but they are not the simplest whole number, right? So if we go back here to get it into a simplest whole number, we just multiply all of the coefficients by 2. And so this is the systematic way I do it because it always works this way. If we got to this last step and it wasn't a fraction, then we'd be done. So this system works every single time. And so just multiply all of the coefficients by 2. So recognize that there is an implied 1 in front of your ethanol. So the coefficients here, I'll do a different color. I'm running out of colors. I don't know, pink, no, red. The coefficient in front of ethanol is 2. The coefficient in front of oxygen is 7. CO2 is 4. And then water is 8. And so the sum would be 21. I think it's 21. Yes, it's 21. Yes. Okay. So there we go. So in that example, there's a fraction of oxygen. If you look at the balancing overview sheet that I have for chapter 1, there are more examples where there aren't fractions, and there are some more examples where there are fractions. So you can try it out, but really it's the same steps over and over: carbon, hydrogen, then oxygen. Yeah, okay. So any questions? Keep going. Keep going. Okay. All right. So more conversions. So the active ingredient in a drug is 2.5 milligrams, so mg. How many of the following masses are equal to 2.5 milligrams? And so it looks like we got the units of mu g. So that funny looking u is a mu, and that means micro. All right, so recognize that this means micro. While m, a small m, means milligram. N means nano. What is this? That's just gram. So that's the base unit. And then the last one is kilo. So my strategy here is just, okay, let's convert milligram to all of these units and see if they match. So what I'm probably going to do here is just convert 2.5 milligrams. Let's convert that to grams first, because that's the base unit that I know. And so we need to ask ourselves, what is the relationship between milli and the base unit? So 1 gram equals 1,000 milligrams, or you can think of it as 1 times 10 to the 3 milligrams. So same thing. So we want to set up this dimensional analysis. So milligrams cancel. So it's 1,000 on the bottom, 1 gram on the top. And so if you do that, I'll just put it into scientific notation because it looks like all of this is in scientific notation. This is 2.5 times 10 to the negative 3 grams. All right, so that's converting milligrams to grams. And so if we compare that, yep, they match. So good, that one is good. So now let's convert to all of the other units as well. So I'll just start with grams because that's the base unit, and I'd have to go to micro, nano, and kilo all in separate steps. That's how I'm going to do it. So we're in grams, so we'll just go left to right. So we have to think, okay, how can we get to micrograms? Right? What's the relationship between gram and microgram? So 1 microgram. So there's a couple ways we can think of it. Micro is really, really small. All right. So you can think of it that there's 1 times 10 to the 6 micrograms in 1 gram. There's a lot of little micrograms in a gram. Also, you can think of it that 1 microgram equals 1 times 10 to the negative 6 grams. These two relationships mean the exact same thing. Be very cognizant of the negative sign. So what this relationship is saying is that a microgram is a tiny, tiny, tiny fraction of a gram. So both of these things it means the same thing. Just stick with one, memorize just one of those prefixes and you'll be good. And recall that micro, it means the same for any unit. So if I was talking about microseconds, we would just change those G's to S's. That's it. So the prefix stays the same for all of those. So now, just like the other one, we think, okay, how do we set up this conversion so the units cancel? So I'll put the microgram part on the top and then 1 gram on the bottom so they cancel. And so when you do that, put that in your calculator. I'll do a different color. This would become 2.5 times 10 to the 3 micrograms. So let's check our answer. Yes, look, they match. Cool. All right, so let's go to nano. Let's go to nano. So I'm going to start with gram again. The gram answer, because that's already in the base unit. So nanogram, so 1 gram is equal to 1 times 10 to the 9 nanograms. So nano is even smaller than a micro. Nano, so small. So small. All right. And so you do that math, it becomes 2.5 times 10 to the 6 nanograms there. Be very sure you can do scientific notation in your calculator. Very sure. So I would check that you are getting all of these things when you put that into your calculator. All right. So is nano right? Yep. Looks like nano is right. So those 3 are right. The last one. So let's convert 2.5 times 10 to the negative 3 grams to kilo. So 1,000 grams is 1 kilogram. And so if we get that, that becomes 2.5 times 10 to the negative 6 kilograms. And so it looks like that one's right too. All right, and so this is how I can make questions, multiple choice questions a little bit more difficult. Like this had many steps to it. All right, and so it wasn't just me saying, okay, like convert milligrams to kilograms and report that number. There are other ways I can kind of ask questions to make it a little bit more complex. And so here, all 4 are equal to 2.5 milligrams. Okay. How do we feel? Oh, there's more questions. I didn't even see it. I didn't see these questions. 2 sig figs. No. Will we have to write the entire equation? I don't know what that means. Do you mean in your work? Write the equation? I mean, I don't care what you do in your work, writing the equation, but it is useful to write the equation. If the question is on an exam, do you have to write an equation? No, because everything is multiple choice. Is that only for combustion doing CHO? Yes, correct. Yes, for only combustion. And then how do we plug in the equation on calculator for question 6 to do 22.9? So what I do is we need to isolate mass. So in my calculator, if you divide both of the sides by these 2 numbers, you put them on the division sign. So this would, see, I'll just erase this. Rewrite this as mass on one side. So I'm going to divide both sides by these numbers. So mass becomes 320 calories over 0.215. I'm going to just drop the units here, divided by 65. And you should get 22.9. All right, so that's just arithmetic, moving division and multiplying things to get them to isolate our variable. So that would be mass in this case. And so if you check the units, sorry, I didn't write them. The unit that comes out is grams. Okay. All right. Sorry, I missed all those things. I didn't know. I'm just one person. Okay. So let's keep going. Chapter 1. Man, it's long. Okay, let's look at this picture and take some measurements. So let's look at this graduated cylinder. What would be an appropriate measurement to report in milliliters? So recall we thought about measurements in terms of significant figures. Measurements have a finite number of significant figures. So the true definition of significant figures is all the numbers we know for certain plus one we estimate. I'm waiting for you to say it. Hopefully you're saying it in your head. It's all the numbers we know for certain plus one digit we estimate. And I think this works perfectly for making measurements like this off of a graduated cylinder, because we can identify, okay, what digits do we know for certain and which one do we estimate? So all of our certain digits comes from the actual markings on the glassware. So if each one of these lines, we need to think to ourselves, you know, how much do each of these lines go up by? So if you look closely here, it looks like they go up by 1. Like we have 10, 11, 12, 13, all the way to 30. It goes up by 1 milliliter. So that means that we know the ones place for certain. We know it with excellent with 100% certainty. I joke, if our line was if our meniscus, okay, I can't zoom in closer, between like 10 and 11, if it was between 10 and 11, you know for certain that the volume is 10 something, that you could bet $1 million that it's 10 something. But within our idea of significant figures is that any measurement is always all the certain digits, everything we know 100% plus 1 digit we estimate. So we always go 1 digit past the markings on any piece of glassware. So if it's marked to the ones place, we always go 1 digit out to the tenths place, so to the 1 decimal place. That would be the appropriate measurement for something like this. And so I know it's cruel, but I say if students, if you would report this number, all right, so this is how I try to trick you. You look at this and you go, oh yeah, that's 24. That's right on the 24 line. So this is 24 milliliters, but that's not correct based upon our idea of significant figures. You can always estimate 1 digit past the markings on your instrument. So this is actually 24.0 milliliters. So that 0 is significant. We estimated it because we know, like by eye, it looks like it's right on that line. So it's 24.0. So it's a little bit cruel of me to say, but I think it's true. And it makes you remember this. If you just write 24 based upon these markings, you're just being lazy. You're being lazy because you always estimate 1 digit past what is marked. So don't be lazy. All right. So for example, if we had another measurement, let's say it was like, so this one is like right on the line, but what if we had something that wasn't on the line? If it was like that, right? So it's kind of in the middle. So that means we have to estimate between those two lines. So I know that this is 25, 26, 27. So I know this is 27 something. 27 is certain, but we always go 1 digit past. So I'm going to say that this is 27.2 milliliters. So what's common here is that both of these values go out to the ones place because that is what's marked within there. Or sorry, the ones place, and then both of them are estimated in the tenths place. So any measurement coming from this specific graduated cylinder will go out to the tenths place, the first decimal place, because we always need to estimate that digit. So if you remember anything with this question, it's don't be lazy with measurements. All right. And so really the strategy here with any type of measurement that you're making, you should first ask yourself, what are the markings on the instrument? Right? So if we had a beaker and they went up by like 10, 20, 30, something like that, we know for certain the tens place. So we would actually be estimating the ones place, essentially estimating, okay, I'm like, 50% between these two lines. So it would be 25 milliliters. So in that instance, because of the markings, the increment of the markings, we would estimate the ones place within there. So that's what you have to keep in mind. Or on a burette, burettes, the markings go up by 1/10 of a milliliter. So that means you actually go out to, you estimate the second decimal place on a burette. So what's the answer? The answer is 24.0. So see, I have 24, but don't be lazy. That's you being lazy, or a student being lazy if they're just reporting 24. It's actually 24.0. Okay, and I put 29 here because I guess note here on this graduated cylinder, only the tens are actually marked with a number, but there are tick marks. So the tick marks count as increments because like that's 21, 22, 23, 24, 25, but they just have the tens like numbered, and that's quite all right. Okay, any questions about measurements? Oh my gosh, there's more questions. I have to scroll down. If the snowstorm is bad, according to our course coordinator, I asked her and she said we will follow OSU's guidelines. So if OSU closes school on Thursday, then we will follow suit, and it will probably, I don't want to say it, but it will probably become a like online take it at home exam, but don't count on that. I was a student here at OSU for 6 years, and the school closed down just once for one day. Okay. Other questions? And we will know pretty soon because your guys' exam is at like noon or like during class on Thursday at 12:45. There's another exam in 12:10 that starts at I think 8 or 9 or something. So they're kind of going to get hit first. So we will find out before then because they have to make a decision for that morning exam people. And then you guys are later. Right. But do anticipate that we have the exam. All right. Okay. All right. Let's keep going. All right. What is the, we did this in class, didn't we? What is the kinetic energy of a baseball traveling at 38 meters per second? Are these the exact same numbers that I did in class? I don't know. So kinetic energy, that is its own equation. Let's ask the peanut gallery. Do you have to memorize the kinetic energy equation? Is that something that has to be memorized? Yes or no? No. Yay. Yes, no. You are given that on your supplemental sheet, but I will write it here for you anyway if you don't have it in front of you. So kinetic energy is equal to 1/2 mv squared, but there is criteria with using this equation. Someone raised their hand. You have to write it in the chat because I can't unmute anyone. The caveat for using this equation is that mass needs to be in kilograms and velocity must be in meters per second. So if you put those two units in, those two variables with those units, then you will get the unit of joules out. That's just how it works. If you inspect the units, it works out. So make sure mass is in kilograms, velocity is in meters per second. So I give you the velocity in meters per second. So good, I don't have to do anything there. But gram, the baseball is in the unit of grams. So I have to convert that to kilograms first. So 141 grams, kilograms. So 1,000 grams is 1 kilogram. So before I put that in the equation, 0.141 kilograms is the mass there. And so at this point, it's just plug and chug. So 1/2 0.141 kilograms times velocity squared. So velocity is 38 meters per second. Make sure you square your 38 and make sure you divide by 2 after multiplying all these things together to get your answer. And so I think the answer is this one. All right, and so this would have 2 sig figs, the answer, whatever is there. And so I definitely, if I had a kinetic energy equation, multiple choice question, the answers would have this not squared. It would have you forgetting to divide by or multiply by the 1/2, and it would have you forgetting to convert it to kilograms. That's how I make the wrong. It's very hard to make wrong answers, right? Because you have to think about, okay, what mistakes will students use? Oh, okay, there's right there. We'll help before the midterm. So I didn't know I have to scroll down. So the supplemental equation sheet is posted already on the midterm preparations page that I supplied to you last week that has all of the keys to the practice midterms. So within that whole page, one of the links is an exact copy of the supplemental packet that you will receive. Okay, all right, so let's keep going. So 10 more minutes. All right. Which molecule contains exactly 11 atoms? So we need to inspect molecules here in the subscripts within them to figure out how many atoms total are in each one of these molecules. So we're looking at subscripts. So this 6 on this attached to this carbon means that a glucose molecule has 6 atoms attached to it. So I'm just going to add up these subscripts. There are 6 carbons. there are 12 hydrogens, and there's 6 oxygens. So total, this glucose has 24 atoms. So that one's not right. All right, so propane. So see how I'm expressing these formulas a little bit different each time, but recognize we're just looking at the subscripts and adding them up. So here's a carbon. There's 1 carbon there. Then there's 3 hydrogens because there's a subscript 3. So 3 there. Then there's there's 1 carbon next. Then there's 2 hydrogens. Oops, that should be a 1. Plus 2 hydrogens plus 1 carbon, and then lastly there's plus 3 hydrogens. So I think if you add all of those numbers up, that is 11. So that is the correct one. But let's just go through some of the weird ones, some other ones here. So ethanol would be 2 plus 5 plus 1 plus 1, because O and H, there's just one of those atoms each. Dopamine, again, check out those subscripts. So 8 plus 11 plus 1 plus 2, whatever that is. And then chloroform, there's 1 carbon, there's 1 hydrogen, and then there's 3 chlorine atoms. I'm just going to add one more. Let's say we had something like something like this. It's not a molecule, but that's okay. Magnesium nitrate. If we had something like this, all right. So recognize that there's 1 magnesium atom right there. And then within NO3, so we don't have to know the charge here. We just are inspecting the subscripts. Within NO3, there's a total of 4 atoms, but there's 2 of those ions. So it's 4 times 2 within there. So to get that sum, it's 1 plus 4 times 2. So whatever that sum is. So keep in mind, when we have a subscript attached to a whole parentheses, it's applied to the entire thing within there. Or if I had something like, if I had like CH3, CH2, and 6 of them, CH3. So another way to think about it is like, okay, there's 4 atoms there. With a carbon and 3 hydrogens. There's another 4 atoms there, carbon and 3 hydrogens. But then there's 6 of these CH units all in a row. That's what that subscript 6 means. And so carbon and 2 hydrogens, there's 3 atoms there, but there's a total of 6 of those units. So the sum for all of those would just be whatever that is. All right. Okay. Other questions? I don't know. Okay, I need to exit out of these. That's why I can't see anything. Okay, what's next? Oh yeah, let's definitely do this one. Okay, so these pictures depict either pure substances, mixtures. So we need to think about our our definitions of those. So do recall those. That pure substances, there's 2 kinds. There's elements and there's compounds. Mixtures, you have a mixture of 2 things that are not chemically combined. So when we ask which pictures depict mixtures, it would be B, C, and E and F. In these 4 pictures, we have different combinations of compounds or molecules or atoms here, and they're not chemically combined. So the idea that this blue and white ball is different than these 2 blue balls, and they're both in like one sample, but they're not chemically combined. That is a mixture, or C in this case, because we have different molecules floating around. Or E and F, we have different atoms floating around there, and they're not chemically combined. So B, C, E, and F are are mixtures. So the next one here, which ones depict pure substances? So recall, pure substance means either an element or a compound. And that has to be the only thing that's in the container. So if we look at these, so kind of the, I guess the hint here is that if it's a mixture, it can't be a pure substance. So it's all the other ones. So A and D are the 2 pure substances. Specifically, A would be an element, and specifically it would be an element that's a molecule, all right? Because there's 2 atoms attached to one another. So this could be something like O2, where oxygen's an element and 2 of them are bonded to one another. And then D, this is also a pure substance, but specifically it's a compound because we have 2 different elements bonded together. But see how they're exactly identical? It's like we took one of those compounds and we just copy and pasted it a bunch of times. That is a pure substance, that each molecule there has the same exact ratio of 1 blue ball and 1 white ball there. All right, so D is a compound and it's a molecule because there's 2 atoms chemically bonded to one another. Okay, which picture depicts a mixture of 2 molecules? Okay, so let's go back to our mixtures. So if we go back to here, E and F are mixtures, but they're atoms. See how there's nothing bonded? It's just 1 atom. So it's not E or F. We want mixtures of 2 molecules. Molecules means at least 2 atoms bonded together. So C has a mixture, but it's a mixture of a molecule and an atom. So this blue ball is an atom. And so B is the correct answer here because we have a mixture of like this would be something like N2, and this would be something like CO. So 2 different molecules or compounds in a mixture together. So molecule just means at least 2 atoms bonded together. Okay, which picture depicts a mixture of 2 elements? So again, thinking about our mixtures again, so B, C, E, or F. Elements, so E and F both have mixtures of atoms, which each represent an element. So I think the answer here is E and F, because if we look at B, we do have an element, but we also have a compound. In C, we also have an element and also a compound. So it's an element and a compound for B and C. So not two elements. Okay, and so finally E, which picture depicts only 1 compound? So again, we're looking at pure substances again, so back to B. So it can only either be A or D. D is the compound because we have 2 different elements bonded together, denoted by the 2 different colors. So I think the answer here is D. Okay, so are there any last minute questions? Any last minute questions? Because I'm gonna go home. Well, no, actually I have to stay and post my thing. Post the thing. So if Caitlin, you said, so since you're a commuter, if the roads are really bad, then the best you can do is just fill out a makeup midterm form. Is the atomic weight and atomic mass the same? You shouldn't need atomic mass. So so the only time we think about atomic mass in this course is the weighted averages. And so yes, atomic weight and atomic mass both refer to the weighted average. Okay, but we do not need to do anything with the mole. Is there any extra credit in this class? No, there's not. Okay, I'm going to stop recording.